Have you ever looked up at the night sky and wondered what bizarre secrets the cosmos might be hiding? The universe is far stranger than we could ever imagine. Black holes that warp time, stars that sing, and galaxies shaped like colossal diamonds. These aren't just science fiction, they're real, and they're out there, waiting to defy everything we thought we knew. Today, we're diving deep into the weirdest corners of space to uncover 30 galactic facts so unbelievable, they'll make you question reality itself. Think about this for a second. Somewhere out there, a planet rains molten glass sideways, whipped by supersonic winds. Or how about a star so dense, a single teaspoon of it would weigh as much as a mountain? The universe doesn't just play by different rules, it rewrites them entirely. And the more we explore, the more we realize how little we truly understand. That's the magic of space. It's an endless well of mysteries, each one more mind-bending than the last. But here's the thing, these aren't just random oddities. They're windows into the sheer scale and creativity of the cosmos, reminding us that reality is wilder than our wildest dreams. From ghostly nebulas where stars are born to supermassive black holes that could swallow entire solar systems without a trace, every discovery pulls back another layer of the universe's grand puzzle. So if you've ever felt that tug of curiosity, that urge to look up and wonder what else is out there, you're in the right place. Buckle up, because we're about to take a journey through the most astonishing, jaw-dropping, and downright bizarre facts the galaxy has to offer. Our galaxy has a secret. It smells like a cosmic cocktail bar. Scientists have discovered that vast clouds of gas and dust drifting through the Milky Way contain ethyl formate, the very same chemical that gives raspberries their sweet, fruity scent and rum its rich, warm aroma. Imagine floating through space and catching a whiff of something that reminds you of a summer fruit stand or a tropical drink. It sounds like science fiction, but it's real interstellar chemistry at work. How do we know this? Radio telescopes picked up the unique molecular signature of ethyl formate in a giant dust cloud near the center of our galaxy. These molecules form in the cold, dark voids between stars, where atoms and particles slowly collide and combine over millions of years. The conditions out there are extreme freezing temperatures, deadly radiation, and near-perfect vacuum. Yet somehow, nature cooks up complex organic compounds in the void. This discovery isn't just a fun fact, it's a clue about how life might have begun. Many of the building blocks of DNA and proteins, like amino acids and sugars, have also been found in space. That means the raw ingredients for life could have been delivered to Earth by comets or meteorites, sprinkling the seeds of biology across our young planet. So the next time you bite into a raspberry or sip a fine rum, remember, you might just be tasting a little piece of the cosmos, but ethyl formate isn't alone out there. Space is full of bizarre molecules, from the buttery scent of diacetyl in distant nebulas to the bitter almond odor of deadly hydrogen cyanide floating between the stars. The universe doesn't just look spectacular, it has a whole cosmic aroma, like some grand interstellar kitchen where the strangest recipes are brewing. And who knows, maybe one day we'll find a region of space that smells like freshly baked bread, because with the universe, anything's possible. If raspberry-scented space clouds weren't strange enough, wait until you hear about the Diamond Planet. Floating about 40 light-years away in the constellation Cancer, there's a world called 55 Cancri E that's literally made of crystallized carbon, essentially a giant cosmic jewel. This super-Earth, twice the size of our own planet, orbits so close to its star that a single year lasts just 18 hours, and surface temperatures could melt iron. But the real shocker, scientists believe its interior may be packed with diamond, forged under crushing pressures that turned carbon into something fit for an interstellar crown. How does a planet like this even form? Most rocky worlds, including Earth, are built from silicates and metals, but 55 Cancri E is a carbon-rich oddball. Its host star contains far more carbon than oxygen, which means the building blocks for this planet were more like graphite and methane than the materials we're used to. Under the immense gravity and heat of its core, that carbon likely compressed into diamond, creating a layer hundreds of miles thick. Picture a world where the bedrock isn't granite, it's gemstone. This discovery flips planetary science on its head. We've long assumed that Earth-like worlds would resemble our own in composition, but 55 Cancri E proves the universe loves variety. There could be entire solar systems out there where planets are made of things we'd consider exotic graphite, diamond, or even stranger carbon-based structures. It's a reminder that the recipes for planet building are far more creative than we ever imagined. And here's the kicker, 55 Cancri E might not be alone. Telescopes have spotted other carbon-heavy worlds, hinting that diamond planets could be more common than we thought. Some might even have layers of liquid carbon or bizarre forms of crystal we've never seen on Earth. So the next time you admire a diamond ring, remember somewhere out there, an entire world sparkles with the same stuff, forged in the heart of a star system unlike anything in our neighborhood. The universe doesn't just create planets, it crafts cosmic jewelry on a scale we're only beginning to understand. Deep in the heart of the Perseus galaxy cluster, something impossible is happening. A black hole is singing. Not with a voice we could ever hear, but with vibrations so deep and slow they ripple through the fabric of space itself. This supermassive black hole, weighing in at hundreds of millions of times the mass of our Sun, has been pulsing out sound waves at a frequency 57 octaves below middle C for over 2 billion years. That's a note so low it would take a piano with keys stretching over 2.5 miles just to reach it. How does a silent vacuum of space produce sound? The secret lies in the superheated gas surrounding the black hole. As material spirals inward, it creates unimaginable pressure, sending shock waves through the surrounding plasma like ripples in a pond. These waves travel outward at incredible speeds, compressing and rarefying the gas in a rhythmic pattern, a cosmic bass note ringing across the universe. NASA Chandra X-ray Observatory detected these pressure waves as subtle changes in brightness within the cluster's gas, translating them into a sound humans could finally perceive by shifting the frequency up by quadrillions of times. What's astonishing isn't just that the black hole sings, it's the sheer power behind that song. The energy carried by these waves is staggering, equivalent to hundreds of millions of exploding stars. Yet to us it's utterly silent. The note's original wavelength is so long, it would take a single vibration over 19 million years to complete one full cycle. Imagine a single cosmic hum lasting longer than all of human evolution. This phenomenon forces us to rethink our assumptions about space. We often picture the universe as a silent, airless void, but in reality, it's thrumming with vibrations, waves of energy passing through dust, gas, and even the emptiness between galaxies. If our ears could detect these ultra-low frequencies, the cosmos would sound like an endless symphony of groaning giants, from colliding stars to the slow spin of pulsars. But for now, we'll have to settle for the translated echoes of Perseus's black hole, a haunting reminder that even in the darkest corners of space, nothing is truly still. And here's the twist, this isn't unique. Other galaxy clusters show similar sound waves, each with its own pitch based on the size and turbulence of the black hole at its core. It's as if the universe has its own choir of invisible bass singers, their voices too deep for any living thing to hear. Yet these vibrations shape the cosmos, heating gas, stirring up star-forming regions, and even slowing the growth of galaxies. So while we'll never stand in space and hear this music firsthand, we now know the universe isn't silent, it's just singing in a key beyond our perception. Right now, as you read this, our moon is inching away from Earth, so slowly you'd never notice, but with consequences that will reshape our world over cosmic timescales. Every year, the moon drifts 3.8 centimeters farther into space, a gentle retreat caused by the gravitational tug of war between Earth and its celestial companion. It might not sound like much, but multiply that by a few billion years, and you've got a solar system that looks radically different from the one we know today. This cosmic slow dance happens because of tides, not just the ocean waves we see, but the invisible stretching of Earth itself. The Moon's gravity pulls slightly harder on the side of our planet closest to it, creating a bulge in Earth's crust and oceans. But since Earth rotates faster than the Moon orbits, that bulge gets dragged a little ahead of the Moon's position. This offset bulge then pulls the Moon forward in its orbit, giving it an energy boost that pushes it farther away. Meanwhile, Earth's rotation slows down in response, like a spinning ice skater extending their arms. Over time, this delicate balance will rewrite Earth's rhythms. Days will stretch longer as our planet's spin continues to slow, eventually matching the Moon's orbital period in about 50 billion years. By then, a single day would last 47 of our current days, with one side of Earth permanently facing the Moon, just like the Moon already shows us only one face. Ocean tides, once powered by the Moon's close proximity, would weaken to a faint ripple, and lunar eclipses, those would become rare cosmic treats, as the Moon's apparent size in our sky would shrink too small to fully cover the Sun. But here's the twist: this process won't last forever. Long before Earth and the Moon become tidally locked, the Sun will have expanded into a red giant, likely engulfing both worlds. That makes the Moon's drift a fleeting chapter in a much grander story, one where even the seemingly permanent fixtures of our sky are just temporary visitors. So the next time you gaze up at the Moon, remember, you're witnessing a slow farewell, a celestial partnership unraveling 1 centimeter at a time across the ages. Far out in the frigid reaches of our solar system, where sunlight is a faint memory and temperatures plunge below -200 degrees Celsius, Neptune hides one of the most dazzling secrets in the cosmos. It rains diamonds. Not metaphorically, not poetically, but literally. The crushing pressures deep within this ice giant's atmosphere are so intense, they can squeeze carbon atoms from methane gas into sparkling diamond crystals. These gemstones don't gently fall, they pelt downward like celestial hailstones, sinking through layers of slushy ice and turbulent gas until they reach the planet's core, where they may accumulate into a vast, molten ocean of liquid carbon. How do we know this happens? Scientists have recreated Neptune's extreme conditions right here on Earth. Using high-powered lasers or diamond anvil cells devices that compress materials between two tiny diamonds, researchers have subjected methane to pressures over 1 million times Earth's atmosphere. At these extremes, the carbon-hydrogen bonds in methane snap, freeing carbon atoms to bond into diamond structures while hydrogen floats away like a ghostly gas. These lab-made diamonds aren't the size of engagement rings. They are microscopic, but the process mirrors what likely occurs in Neptune's depths. What's even wilder: these diamond showers might not be unique to Neptune. Uranus, another ice giant, probably experiences the same phenomenon, and some exoplanets, those distant worlds orbiting other stars, could have diamond rainstorms so intense they form layers of solid diamond hundreds of miles thick. Imagine entire planetary mantles glittering with compressed stardust, a geological spectacle beyond anything in our solar system. But here's the twist: we've never directly observed this diamond rain. Neptune's thick atmosphere obscures our view, and no probe has ever penetrated deep enough to snap a photo of this glittering tempest. Instead, we piece together clues from spectroscopy, lab experiments, and computer models. That means every time you see an artist's illustration of diamond rain on Neptune, you're looking at an educated guess, a scientific daydream based on physics and chemistry we're still unraveling. This discovery changes how we see these distant worlds. Neptune isn't just a blue marble of freezing gas, it's a factory for cosmic alchemy, where simple molecules transform into precious gems under forces we can barely comprehend. It's a reminder that the universe doesn't just create beauty, it forges it in the most violent, extreme environments imaginable. So the next time you admire a diamond, remember, somewhere out there, whole storms of them are falling into the dark, a glittering cascade hidden in the clouds of a world we've barely begun to understand. Hidden beyond the Milky Way's dusty veil, a cosmic mystery tugs at our entire galactic neighborhood with the force of 10,000 suns, the Great Attractor. This enigmatic gravitational anomaly, located roughly 250 million light-years away in the direction of the constellation Centaurus, is pulling galaxies, including our own, toward it at a staggering speed of 14 million miles per hour. Yet despite its overwhelming influence, we can't see it directly because it lies buried behind what astronomers call the zone of avoidance, a region of space obscured by the dense stars, gas, and dust of our galaxy's disk. What makes this invisible force so puzzling? For decades, scientists have pieced together clues from the motion of galaxies, noticing that everything within a mind-boggling volume of space, spanning hundreds of millions of light-years, flows toward this single point like water spiraling down a drain. The Great Attractor's gravitational pull suggests it should be a massive supercluster of galaxies, yet when researchers peered through infrared and radio telescopes to bypass the Milky Way's obstruction, they found only a fraction of the expected mass. That means something even bigger, something we still can't fully explain, must be lurking in the shadows. Recent discoveries have deepened the intrigue. The Great Attractor itself appears to be moving, pulled toward an even more colossal structure, the Shapley supercluster, the most massive known concentration of galaxies in our cosmic vicinity. This suggests we're witnessing a cosmic tug-of-war on an unimaginable scale, where gravity's invisible strings connect everything in a vast web of motion. But the Great Attractor remains the closer, more immediate puzzle, one that challenges our understanding of how matter is distributed across the universe. Why hasn't this mystery been solved yet? The zone of avoidance isn't just a minor obstacle, it blocks nearly 20% of the sky from optical telescopes, creating a literal blind spot in our cosmic maps. Only by using wavelengths like X-rays and radio waves, which penetrate dust, have astronomers glimpsed hints of galaxy clusters hiding there. Even then, the data is patchy, like trying to reconstruct a city skyline from scattered flashlight beams in thick fog. This isn't just academic curiosity. The Great Attractor reshapes our place in the cosmos. Our local galaxies aren't drifting aimlessly. They're part of a grand, directed flow, like leaves caught in a river current. And if the Great Attractor's true nature defies expectations, perhaps hiding unseen dark matter or unknown structures, it could rewrite the rules of galactic motion. For now, it remains one of astronomy's most tantalizing riddles, a reminder that even as we map the universe, some of its biggest secrets are still hiding in plain sight, just beyond our line of view. Somewhere in the constellation Libra, a star silently burns with a secret that defies our understanding of time itself. HD 140283, nicknamed the Methuselah star, flickers with an age astronomers estimate at over 14 billion years, a number that sends shockwaves through cosmology because it's older than the universe's currently accepted age of roughly 13.8 billion years. At first glance, this isn't just a puzzle, it's an impossibility. How can a star exist before the cosmos itself? The key lies in the margin of error. When scientists first calculated Methuselah's age using its composition, brightness, and motion, the range stretched from 13.5 to over 15 billion years, overlapping uncomfortably with the universe's timeline. This triggered a re-evaluation of every assumption from the star's distance, revised slightly closer, making it younger to the models tracking its evolution. Updated measurements now place it around 13.7 billion years, just shy of the cosmic limit, but the tension hasn't entirely vanished. What makes this star such a stubborn outlier? Unlike most ancient stars, Methuselah contains more heavy elements like oxygen and iron than expected for its age, suggesting it formed from material already enriched by earlier generations of stars. That's forced astronomers to tweak their understanding of how quickly the first stars could have seeded the cosmos with heavier elements. Some even speculate it might be a rare survivor from a predecessor universe, a cosmic relic from before the Big Bang, though that remains firmly in the realm of theoretical speculation. But the real revelation here isn't just about one star's age, it's about the flexibility of science itself. When observations clash with theory, it doesn't mean one is wrong, it means our models need refining. Each adjustment brings Methuselah's story closer to the cosmological timeline while teaching us something new about stellar evolution. Perhaps the star's turbulent history, ejected from a dwarf galaxy stretched by galactic tides, skewed early readings. Or maybe the universe's expansion rate needs another look. This cosmic detective work highlights how science thrives on anomalies. Methuselah isn't an error to erase, it's a guidepost pushing us to ask deeper questions about time, the early universe, and the very limits of our knowledge. After all, if a single star can challenge everything we thought we knew, what other surprises might be hiding in the dark? While most planets pirouette gracefully in the same direction they orbit the Sun, Venus dances to its own rhythm, backward. This celestial rebel spins clockwise, a motion astronomers call retrograde rotation, while nearly every other planet, including Earth, twirls counterclockwise. If you stood on Venus's scorching surface, not that you'd want to, the Sun would rise in the west and set in the east, defying everything we consider normal in our solar system. But the oddities don't stop there. A single Venusian day lasts longer than its year, 243 Earth days to complete one rotation, but only 225 to circle the Sun. Picture a world where your birthday comes around faster than your sunrise. Why does Venus spin backward? The leading theory points to cosmic violence in its past. Billions of years ago, a colossal impact, perhaps with a proto-planet the size of Mars, might have struck Venus with such force, it flipped the planet's rotation entirely. Think of a spinning top getting smacked sideways. The disruption could have sent Venus into its sluggish, backward whirl. Others suggest gravitational tugs from the Sun's intense heat and atmospheric tides. The same forces that slow its spin today gradually reversed its direction over eons. But here's where things get even stranger. Venus's retrograde spin isn't its only quirk. Its atmosphere moves 60 times faster than the planet itself, whipping around in just 4 Earth days compared to the surface's snail-paced rotation. This creates supersonic winds that scream across the planet at over 200 miles per hour, dragging thick clouds of sulfuric acid along like a runaway carousel. The contrast between Venus's leisurely spin and its hellish surface conditions is jarring. While the planet ambles through its day-night cycle, temperatures soar to 870 degrees Fahrenheit, hot enough to melt lead, thanks to a runaway greenhouse effect. Carbon dioxide blankets the planet, trapping heat like a suffocating oven. So while Venus might seem serene from afar, its slow, backward waltz hides a world of chaos beneath those reflective clouds. This backward ballet forces us to reconsider how planets evolve. Venus isn't just an oddity, it's a cautionary tale. Earth could have easily shared its fate had conditions been slightly different. By studying Venus's twisted rotation and toxic atmosphere, we glimpse alternative paths a planet's life might take, reminding us that even in the orderly solar system, chaos leaves its mark. Floating 12 billion light-years away, a cosmic leviathan holds a secret that reshapes how we think about water in the universe. The quasar APM 08279 plus 5255 isn't just one of the most luminous objects in existence, it's also home to the largest known reservoir of water, a vapor cloud containing 140 trillion times all the water in Earth's oceans combined. That's enough to fill every drop of every sea, lake, and ice cap on our planet 140 trillion times over. And this isn't liquid water or ice, it's a swirling, superheated mist enveloping the quasar's active supermassive black hole, stretching hundreds of light years across. How does something so unimaginably wet exist in the depths of space? Quasars like APM 08279 are the universe's ultimate powerhouses, galaxies with voracious black holes at their cores, devouring matter so fiercely they outshine every star in their galaxy combined. As material spirals toward the black hole, it forms an accretion disk of searing gas and dust radiating unimaginable energy. Surrounding this inferno, vast clouds of water vapor thrive in the chaos, energized by the quasar's intense radiation. The water molecules here don't pool or freeze, they vibrate furiously, glowing in the infrared spectrum as they absorb and re-emit light. What's truly mind-blowing isn't just the scale, it's the timing. This quasar exists in the early universe, just 1.6 billion years after the Big Bang. That means vast quantities of water formed astonishingly quickly, long before our solar system even existed. The discovery shattered assumptions about how soon complex molecules could emerge in cosmic history. Water, it turns out, isn't a rare luxury, it's a universal constant, appearing even in the most hostile environments imaginable. But here's the twist, this isn't just a cosmic curiosity. Water reservoirs like this could be the cradles of life across the cosmos. When quasars eject material through powerful jets, they scatter water-enriched clouds across intergalactic space. These molecules might eventually settle into forming planetary systems, seeding young worlds with the essential ingredient for biology. Imagine every glass of water you've ever drunk could trace its lineage back to violent, ancient events like this, where supermassive black holes acted as accidental alchemists, forging the building blocks of life in their fury. The implications ripple outward. If water was this abundant so early in the universe, then the conditions for life might have existed far longer and in more places than we ever dreamed. Planets orbiting distant stars could have inherited their oceans from quasars like APM 08279, meaning life's potential isn't confined to quiet, stable systems. It might thrive even in the aftermath of cosmic cataclysms. So while we'll never drink from this 12-billion-year-old reservoir, its existence whispers a profound truth. Water, and perhaps life itself, is written into the fabric of the universe in ways we're only beginning to understand. Imagine a star moving so fast it could cross the distance from New York to Los Angeles in less than 5 seconds. That's the mind-bending reality of hypervelocity stars. These cosmic speedsters rocket through space at over 1 million miles per hour, so fast they've escaped the gravitational grip of their home galaxies entirely. Unlike every other star bound to the Milky Way's spiral arms, these rogue travelers are on a one-way trip into the abyss between galaxies, destined to drift forever in darkness. The secret to their incredible speed lies in a violent dance with a supermassive black hole. When a binary star system, two stars orbiting each other, wanders too close to a black hole like the one at our galaxy's center, the black hole's gravity can tear the pair apart. One star gets captured into orbit while the other is flung outward at unimaginable velocity, like a slingshot releasing its projectile. The energy transferred in this cosmic breakup is so extreme, the ejected star becomes a galactic fugitive, racing toward intergalactic space at up to 3 times the speed needed to escape the Milky Way's pull. Spotting these stellar runaways isn't easy, but astronomers have a clever tool, the Doppler effect. As a hypervelocity star streaks away from us, its light stretches slightly toward the red end of the spectrum, like the fading whistle of a speeding train. By measuring this redshift with precision instruments, scientists can calculate not just the star's speed but often trace its path back to the galactic center, confirming its dramatic origin story. The fastest known hypervelocity star, S5 HVS1, is barreling outward at over 4 million miles per hour, so fast it will leave our galaxy within 100 million years. What's truly humbling is imagining these stars' ultimate fate. With no galaxy to call home, they'll traverse the freezing void for billions of years, their light growing dimmer as they drift ever farther from any celestial neighbors. Some might eventually pass near another galaxy, only to continue their lonely journey. Others could become frozen relics in intergalactic space, their cores still burning long after their home galaxy's stars have flickered out. This phenomenon forces us to rethink what it means to be part of a galaxy. We assume stars live and die within the systems that birth them, but hypervelocity stars prove the cosmos is far more dynamic and far more willing to fling its children into the unknown. Each one is a testament to the raw power lurking at galactic centers, where black holes don't just consume matter, but occasionally catapult it across the universe. Jupiter's Great Red Spot isn't just a storm, it's a planetary beast, a swirling vortex of gas so vast it could swallow Earth whole with room to spare. For at least 400 years, this crimson hurricane has churned in Jupiter's upper atmosphere, sustained by jet streams moving at 300 miles per hour. But lately, astronomers have noticed something unsettling. The storm is shrinking. What once measured 25,000 miles across in the late 1800s, wide enough to fit 3 Earths side by side, now spans barely 10,000 miles, and it's growing taller as it narrows, like a spinning top wobbling toward its final moments. Why does Jupiter's most famous feature behave this way? The answer lies in the gas giant's chaotic atmosphere. Unlike Earth's hurricanes, which weaken when crossing land or cool waters, the Great Red Spot has no solid surface to disrupt it, just endless layers of hydrogen and helium. Instead, its changes come from interactions with smaller storms that constantly batter its edges, stealing energy and momentum. Some researchers believe these flakes, breaking off the main storm, resemble cells in a lava lamp, redistributing heat and material in ways we don't yet fully understand. What's truly bizarre is the storm's color. While most of Jupiter's atmosphere shows muted tans and blues, the Great Red Spot burns with a distinctive brick red hue. Scientists suspect complex chemical reactions are at work, perhaps sunlight breaking apart ammonia and hydrogen sulfide compounds, creating sulfur-rich molecules that absorb blue light. Or maybe the storm dredges up deeper material from Jupiter's unseen layers, like a cosmic blender exposing hidden ingredients. Either way, its vivid appearance makes it one of the solar system's most striking landmarks. Will the Great Red Spot vanish entirely? Current models suggest it might stabilize at a smaller size rather than disappear completely, but there's no guarantee. Some smaller white ovals, similar storms on Jupiter, have merged or dissipated over decades, showing how fluid atmospheric dynamics can be. If the spot does fade, it would mark the end of an era. Galileo might have glimpsed this storm through his crude telescope in 1610, and every generation since has seen it watching back from Jupiter's face like an unblinking eye. What's often overlooked is how this storm defies our expectations of time. 4 centuries is an eye blink compared to Jupiter's 4.5 billion-year history, yet human civilization has never known a world without this tempest. Its endurance hints at the unimaginable scales of gas giant weather, where storms aren't passing events but near-permanent features. As we watch the Great Red Spot evolve, we're really glimpsing the heartbeat of a planet, a reminder that even the most familiar cosmic sights are anything but static. The moon's serene, cratered face hides a fiery secret. It was once a world of raging volcanoes, and their remnants could be the key to humanity's future there. While we've long known about dark patches called Maria, ancient lava plains that formed billions of years ago, recent discoveries reveal volcanic activity may have flickered on the moon as recently as 100 million years ago. That's shockingly recent in cosmic terms, back when dinosaurs still roamed Earth. The smoking gun, strange formations called irregular mare patches or IMP scattered across the lunar surface. These blister-like mounds, some no larger than a city block, are surrounded by crisp, young-looking terrain devoid of the usual bombardment scars. It's as if patches of lava oozed onto the surface yesterday, preserving landscapes in geologic time capsules. But the real treasure lies beneath the surface: lava tubes, collapsed tunnels left behind by ancient volcanic flows, snake under the moon's crust like cosmic subway systems. Some stretch for dozens of miles, with ceilings high enough to fit the Statue of Liberty. These tunnels formed when molten rock cooled at the surface, creating a roof while lava still rushed underneath. Once the flow stopped, hollow conduits remained, shielded from meteors, radiation, and temperature swings that batter the lunar surface. Thermal imaging from orbit reveals these hidden voids, some with stable temperatures around -20 degrees Celsius balmy compared to the surface's 300-degree swings between day and night. Why does this matter for colonization? These lava tubes could be nature's perfect lunar bunkers. Future astronauts wouldn't just camp in them. Entire underground bases could flourish, with thick rock ceilings deflecting deadly cosmic rays and micrometeorites. Solar panels on the surface could feed power below, while ice deposits at the poles might supply water. Some tubes are so vast they could house pressurized habitats mimicking Earth's atmosphere, even allowing for vertical farming under artificial sunlight. It's not science fiction. NASA's Artemis program already targets lunar lava tubes as prime real estate, and private companies are designing robots to map them before humans arrive. The twist: this volcanic legacy might not be unique to our moon. Mars, Mercury, and even some asteroids show evidence of similar lava tubes, hinting that nature's blueprint for off-world shelters could be universal. So while we once saw the moon as a dead rock, its volcanic whispers now guide our next giant leap, turning celestial geology into humanity's stepping stones for the stars. Galaxies shouldn't defy gravity's rules, but NGC 1052DF2 does exactly that. This faint, ghostly galaxy drifting in the constellation Cetus is missing something fundamental to cosmic architecture: dark matter. That's like finding a skyscraper without steel beams or an ocean without water. Every other galaxy we've observed relies on this invisible, mysterious substance, which outweighs normal matter 5-to-1 to hold itself together. Without dark matter's gravitational glue, galaxy formation as we know it shouldn't be possible. Yet here's NGC 1052DF2, spinning lazily through space with stars moving so slowly that visible matter alone accounts for all its gravity. How did astronomers stumble upon this cosmic rule breaker? The discovery came from studying the motion of 10 ancient star clusters orbiting the galaxy. Using Hawaii's Keck Observatory, researchers measured their velocities and got a shock: they were crawling compared to predictions. In a normal galaxy, dark matter's pull would accelerate these clusters to dizzying speeds, but here they ambled along like sleepy commuters. Follow-up observations with the Hubble Space Telescope confirmed the impossible. NGC 1052DF2's mass matched its visible stars and gas almost perfectly, leaving no room for dark matter's gravitational shadow. This revelation tore through astrophysics like a lightning bolt. Either dark matter isn't as universal as we thought, or this galaxy underwent something bizarre in its past. Some theorists suggest a catastrophic collision billions of years ago might have stripped away its dark matter, like cosmic thieves robbing a bank vault. Others propose it formed differently, perhaps from gas ejected during a violent galactic merger, leaving it stillborn without the dark matter scaffolding typical galaxies require. But the most radical idea, that NGC 1052DF2 hints at flaws in our understanding of gravity itself, suggesting alternative theories like modified Newtonian dynamics might explain its behavior without invoking dark matter at all. The plot thickened when another dark matter-deficient galaxy, NGC 1052DF4, was found nearby. Two oddballs in the same neighborhood can't be coincidence. There must be a mechanism creating these enigmas. Yet studies of their host group show no signs of recent violence that could explain dark matter theft. This leaves scientists wrestling with an uncomfortable truth. Either our models of galaxy formation are incomplete, or dark matter behaves in ways we've never imagined. What makes this debate so electrifying is what it reveals about scientific progress. Anomalies don't break theories, they refine them. Whether NGC 1052DF2 is a cosmic accident or a signpost to new physics, its existence proves the universe still holds cards we haven't seen. Every time we think we've grasped the rules, something like this winks back at us from the void, whispering that the story is far from over. At Saturn's North Pole, the laws of planetary weather take a sharp turn, literally. While most storms swirl in circular hurricanes or chaotic vortices, Saturn boasts something utterly alien, a perfect hexagon big enough to fit 4 Earths side by side. This 6-sided jet stream has raged for at least 4 decades, maybe centuries, its razor-straight edges defying everything we know about fluid dynamics. The polygon sides stretch nearly 9,000 miles each, with winds screaming at over 200 miles per hour, yet the shape remains eerily stable, like a cosmic honeycomb stamped into the clouds. What causes such geometric precision in a gas giant's atmosphere? The leading theory points to deep-rooted turbulence, Saturn's rapid rotation. A day lasts just 10.5 hours combined with varying wind speeds at different latitudes might create standing wave patterns. Picture water swirling around a drain. Under certain conditions, interference between fast and slow-moving layers can produce stable geometric shapes rather than smooth curves. Laboratory experiments with spinning fluids have recreated similar polygons, suggesting Saturn's hexagon is essentially a gargantuan version of a physics classroom demonstration, scaled up to planetary proportions. But here's where it gets stranger. Unlike Jupiter's Great Red Spot, which changes size and color over time, Saturn's hexagon has maintained its shape with uncanny consistency since Voyager first spotted it in 1980. Cassini's later missions revealed the hexagon extends hundreds of miles deep into the atmosphere, with towering walls of cloud stacked like layers in a wedding cake. Even more bizarre, the storm's color shifts with Saturn's seasons, changing from golden hues to a deep cerulean as sunlight angles shift over its 30-year orbit. Not everyone agrees on the hexagon's origins. Some researchers propose it's a manifestation of deep atmospheric jets interacting with Saturn's internal magnetic field, effectively printing the shape onto the upper clouds. Others suggest it might be a type of Rossby wave, a planetary scale vibration familiar on Earth as the wiggles in our jet stream, amplified by Saturn's lack of solid topography to disrupt the flow. The wildest hypothesis, that the hexagon marks the footprint of some exotic form of convection occurring in Saturn's liquid metallic hydrogen interior, thousands of miles below the visible cloud tops. What makes this storm truly unique is its mathematical purity. Nature loves efficiency, think of honeycombs or snowflakes, but Saturn's hexagon operates on a scale where we'd expect chaos to dominate. Instead, it's as if the universe decided to carve a perfect stop sign into the side of a gas giant, just to remind us how little we truly understand about planetary atmospheres. As we search for exoplanets, discoveries like this force us to reconsider what normal weather looks like on worlds beyond our own. Perhaps hexagonal storms are common out there, and Saturn is just the first place we've noticed them. Until we find another, this 6-sided enigma remains one of the solar system's greatest atmospheric mysteries. For decades, astronomers have faced a cosmic detective story, one where the clues keep leading to empty hands. When they tally up all the visible stars, galaxies, and gas clouds, nearly half the universe's ordinary matter, the protons, neutrons, and electrons that make up everything we can touch, is missing. Not dark matter, but real, tangible stuff that should be there, yet somehow evades detection. This lost baryonic matter isn't hiding in black holes or floating between galaxies as rogue planets. Instead, scientists now believe it's threaded through space in an invisible web of superheated gas filaments, so diffuse and energetic that our telescopes barely sense its presence. How do we know this missing matter exists at all? The answer lies in the afterglow of the Big Bang. By studying the cosmic microwave background, the faint radiation left over from the universe's infancy, scientists can calculate exactly how much ordinary matter should be present. The numbers don't lie. About 5% of the cosmos should be baryonic. Yet when we count up all the stars, dust, and detectable gas, we only account for roughly half that amount. The rest must be lurking somewhere just beyond our current observational reach. Recent breakthroughs suggest this elusive material takes the form of WIM, the warm, hot intergalactic medium. Picture an invisible scaffolding stretching between galaxies, composed of gas heated to millions of degrees but spread so thin, a cubic meter might hold just a few atoms. At these temperatures, the gas glows faintly in X-rays, but its signal drowns in the cosmic noise. Only when distant quasars' ultra-bright galactic cores shine their light through these filaments do we get hints of their presence. Like finding a whisper in a hurricane, astronomers detect slight dips in the quasar's light where WIM absorbs specific wavelengths, revealing the fingerprints of oxygen and nitrogen ions floating in the void. The challenge in mapping this cosmic web isn't just technological, it's conceptual. These filaments are so vast and tenuous that a single structure might span millions of light years while weighing less than a handful of Earth's atmosphere. Some simulations suggest the missing matter could also hide in galactic winds, colossal streams of gas blown outward by star formation and black hole activity. These outflows, rich in heavy elements, might cool and fade into obscurity beyond galactic edges, slipping past our observational nets. What's thrilling isn't just solving the mystery, it's realizing how much of the universe remains hidden in plain sight. The same way Earth's oceans hold more undiscovered species than known ones, the cosmos brims with matter we're only beginning to trace. Future telescopes like ESA's Athena X-ray Observatory aim to illuminate these shadowy structures, turning faint whispers into detectable signals. Every filament mapped brings us closer to balancing the universe's ledger, and who knows what other secrets might lurk in those glowing threads between the stars. We tend to think of planets as obedient children, forever orbiting their parent stars, but the universe loves rule breakers. Drifting through the interstellar void, invisible to traditional telescopes, countless rogue planets wander alone in eternal night. These cosmic orphans, flung from their birth systems by gravitational chaos or born in the cold collapse of gas clouds without a star to call home, may outnumber all the stars in our galaxy by 20 to 1. That means for every twinkling dot you see in the night sky, there could be 20 frozen, airless worlds sliding silently through the dark. Detecting these nomads is like finding a black cat in a coal cellar. Without starlight to illuminate them, they're nearly invisible except for one peculiar cosmic trick: microlensing. When a rogue planet passes precisely between Earth and a distant star, its gravity bends and magnifies the star's light like a frosted glass lens. For a few hours or days, the background star flares brighter in a telltale curve before fading back to normal. It's not the planet we see, it's the ghostly fingerprint of its gravity warping spacetime itself. The numbers from microlensing surveys are staggering. Observations suggest our Milky Way alone could host hundreds of billions of rogue planets, outnumbering stars so dramatically they've rewritten our understanding of planetary formation. Some are gas giants ejected during the violent youth of their systems, when young planets jostle for position like marbles in a spinning tray. Others might be failed stars, substellar objects too small to ignite fusion, condemned to wander as cooling embers. The most haunting possibility, Earth-sized rogues frozen at -200 degrees Celsius, their subsurface oceans locked under miles of ice, drifting for eternity without a sunrise. What's truly unsettling is imagining the journey of these worlds. a rogue planet cast adrift billions of years ago might have crossed intergalactic space by now, flung beyond the Milky Way's grasp. Others could pass through our solar system unnoticed, their presence betrayed only by subtle tugs on the Oort cloud's comets. And if any carry life, perhaps in deep, radioactive heated oceans shielded by ice, it would be the ultimate cosmic isolation, evolving in perpetual darkness with no sky to gaze upon. This discovery shatters our planet-centric worldview. We assume life needs a star's warmth, but rogue planets hint at alternatives: biology persisting in eternal night, powered by geothermal vents or decaying atoms. Future telescopes could hunt for the faint heat signatures of nearby rogues, and who knows what we'll find. The universe clearly has a soft spot for runaways, and these dark wanderers might be its most common children, silent, unseen, and endlessly roaming the abyss between the stars. Right now, the sun burns with the fury of nuclear fusion, a seething ball of plasma where hydrogen atoms crash together to form helium in a cosmic cauldron. But trillions of years from now, long after its final death throes, our star will undergo a transformation more surreal than any sci-fi tale. Its core will slowly freeze into a crystallized sphere, a celestial diamond the size of Earth. This isn't poetic exaggeration, it's the inevitable fate of all but the most massive stars, a final act written into the laws of physics. Before this eerie metamorphosis, the sun will blaze through its more dramatic phases. In about 5 billion years, it'll swell into a red giant, engulfing Mercury, Venus, and likely Earth itself, its outer layers stretching far beyond Mars' orbit. For a brief cosmic moment, it'll shine thousands of times brighter, cooking any surviving worlds with relentless radiation. Then, like a candle guttering out, it'll shed those outer layers in a glowing planetary nebula, leaving behind only its exposed core, a white dwarf no larger than Earth but packing half the sun's original mass into a searing hot ember. Here's where the real magic begins. Over mind-boggling timescales, this white dwarf will cool from a blistering 100,000 degrees to a mere few thousand. Its interior electrons squeezed so tightly they enter a quantum state called degenerate matter. As the temperature continues to plummet, those electrons can't pack any tighter instead. The star's carbon and oxygen ions begin arranging themselves into an orderly lattice, just like the carbon atoms in a diamond. The crystallization starts at the core and spreads outward over billions of years, turning the entire stellar remnant into a planet-sized crystal of solid oxygen and carbon, glittering in the perpetual night of deep time. What's astonishing isn't just this crystalline fate, it's the contrast with the sun's earlier violence. The same star that once bathed planets in life-giving light and later vaporized them becomes a cosmic ice cube, its internal heat slowly leaking away into the void. The diamond metaphor isn't perfect. This crystal would be far denser than any earthly gem, with a teaspoon weighing several tons, but the principle holds. Some white dwarfs we've observed today, like BPM 37093, already show signs of this process beginning, their interiors potentially containing crystallized cores larger than Earth. Yet even this crystal corpse won't last forever. Given enough time, far beyond the current age of the universe, the sun's remnant will cool to near absolute zero, becoming a black dwarf, a cold, dark crystal adrift in an expanding cosmos. By then, the universe itself may have transformed beyond recognition, with galaxies evaporated by dark energy and protons decayed into radiation. Our sun's diamond core could be one of the last relics of this cosmic era, a frozen tombstone for a solar system long forgotten. This duality, the sun's fiery grandeur and its frozen afterlife, forces us to rethink time itself. We measure stars in billions of years, but their remnants play out over trillions, persisting long after their light fades. And though we'll never witness this crystalline twilight, its inevitability hints at a universe far stranger than we imagine, where even stars become frozen artifacts in a museum of cosmic history. In the depths of space, some stars don't just shine, they flash like cosmic lighthouses with such perfect rhythm. They were once mistaken for alien distress signals. These are pulsars, the rapidly spinning corpses of massive stars that exploded as supernova. What remains is a neutron star so dense, a sugar cube-sized piece would weigh as much as Mount Everest. But their real magic lies in how they beam radiation into space like a spinning searchlight, creating pulses so regular they rival atomic clocks. The story begins in 1967 when Cambridge researcher Jocelyn Bell noticed an unusual signal in her radio telescope data, a series of sharp, repeating blips spaced exactly 1.337 seconds apart. The pulses were so unnervingly precise, her team briefly labeled them LGM-1, short for Little Green Men. Could this be an interstellar beacon from an advanced civilization? The truth proved even more extraordinary. They discovered the first pulsar, a neutron star spinning furiously while its powerful magnetic fields funneled radiation into narrow beams from its poles. Like a lighthouse beam sweeping past a ship, these jets appear to pulse when they point toward Earth, vanishing when they swing away. What makes pulsars truly mind-bending is the physics behind their blink. As the star's intense magnetic field accelerates particles near its surface, they spiral along field lines and blast outward as focused radiation, usually radio waves, though some pulsars emit X-rays or gamma rays. The pulse we detect isn't the star turning on and off, it's our perspective catching the edge of these rotating beams. Some spin hundreds of times per second, making them the universe's most precise natural timekeepers. The Crab pulsar, born in a supernova observed in 1054 AD, whirls 30 times every second, while the record holder PSRJ 17-4307 completes 716 rotations in the same blink of an eye. Yet the first pulsar's discovery almost didn't happen. Bell noticed the signal buried in miles of paper chart recordings, a faint anomaly others might have dismissed as interference. Her persistence uncovered a phenomenon that now helps us test Einstein's gravity, map the galaxy, and even guide spacecraft. Future missions like NASA's A Nicer Experiment use pulsar X-rays as cosmic GPS signals, proving that sometimes the universe's strangest quirks become humanity's most useful tools. The irony, these dead stars shine brighter in death than they ever did in life. Their relentless ticks will outlast civilizations, outshine their former stellar glory, and keep flashing long after every human monument has crumbled to dust. So while Jocelyn Bell's Little Green Men turned out to be something even more incredible, they remind us that the universe often saves its greatest wonders for its most unlikely survivors. While the planets in our solar system often seem frozen in time, Mercury tells a different story. It's shrinking before our eyes. This tiny world, battered by solar radiation and scorching temperatures, has been quietly contracting for billions of years as its massive iron core cools and solidifies. The result, a surface crisscrossed with towering cliffs hundreds of miles long, some as high as Mount Everest, where the crust has crumpled like the skin of a dried-up raisin. These scarps, known as lobate thrust faults, snake across Mercury's landscape, marking the spots where sections of the planet's brittle outer shell have fractured and stacked atop one another as the interior loses volume. What makes Mercury's contraction so dramatic compared to Earth's? The answer lies in the planet's unusual anatomy. Mercury's core makes up a staggering 60% of its mass, far larger proportionally than Earth's, meaning even small changes in temperature have planet-wide consequences. As this immense metallic heart gradually cools, it contracts, pulling the overlying mantle and crust inward like a deflating balloon. NASA, a messenger spacecraft, mapped over 30,000 of these faults during its mission, revealing a world more geologically restless than anyone expected. Some scarps are young enough to suggest the shrinking continues today, making Mercury the only planet besides Earth known to display active tectonic processes. Yet this isn't just a scaled-down version of Earth's plate tectonics. While our planet recycles its crust through subduction zones and mid-ocean ridges, Mercury's contraction creates a one-way process. The crust cracks, buckles, and piles up with nowhere to go. Imagine a pie crust hardening as it cools, then cracking because the filling beneath has shrunk, except this pie is 4,000 kilometers wide, and the cracks could swallow whole mountain ranges. The most striking of these features, Enterprise Roops, stretches over 600 miles and climbs nearly 2 miles high, a planetary wrinkle frozen in time. The irony, this shrinkage might explain why Mercury, despite being the closest planet to the Sun, has a weaker magnetic field than distant Earth. A slower cooling core would remain more molten, generating stronger magnetic dynamos, but Mercury's rapid contraction suggests its core is cooling faster than predicted, leaving less churning metal to power its magnetic shield. It's a cosmic feedback loop. The smaller the planet gets, the more it loses the very protection that could have preserved its ancient atmosphere or surface ices in shadowed craters. As we study these wrinkles, we're glimpsing a future that might await Earth billions of years from now. Our planet's core will eventually cool too, though far more slowly thanks to its insulating mantle and radioactive heating. When it does, could continents buckle like Mercury's crust, or will plate tectonics find another path? For now, this tiny, shrinking world serves as a reminder that even planets age, their surfaces bearing the scars of time just as our skin wrinkles with years. The difference, Mercury's wrinkles tell the story of a cooling heart, written across a landscape that hasn't stopped changing since the solar system's birth. Right now, two cosmic titans are locked in a slow-motion dance that will redefine our galactic future. The Milky Way and Andromeda, hurtling toward each other at 250,000 miles per hour. In about 4.5 billion years, these spiral giants will meet in a collision of unimaginable scale, merging into a single, colossal galaxy. But don't picture stars smashing like cars in a cosmic pileup. Space is so vast that even during this billion-year merger, direct stellar collisions will be almost non-existent. Instead, gravity will weave a new tapestry from both galaxies, stretching their arms into glowing streams and eventually settling into a serene, elliptical galaxy some astronomers have nicknamed Milky Way. What's fascinating isn't just the eventual merger, it's how little danger it poses to Earth's distant descendants. The average distance between stars in a galaxy is so vast, about 4 light-years in our neighborhood, that even when galaxies overlap, stars slip past each other like ships in an endless ocean. Solar systems might drift into new orbits, but the chances of a foreign star barreling into ours are astronomically slim. The real transformation will happen to the galaxies themselves. As Andromeda's gravity tugs at the Milky Way's spiral arms, vast waves of gas and dust will compress, triggering fireworks of new star formation. Imagine cosmic brushstrokes of blue-white young stars painting across the sky, visible even in daylight from any surviving worlds. Yet this merger has already begun in a way we're seeing Andromeda as it was 2.5 million years ago due to light's travel time. Right now, the real Andromeda is even closer, its gravity subtly distorting the Milky Way's outer halo of dark matter. Future astronomers won't just watch the collision unfold, they'll live inside it, with Andromeda filling the night sky as it approaches, its spiral arms growing from a faint smudge to a shimmering cosmic whirlpool. Over millennia, the two galaxies will pass through each other multiple times, like pendulums losing energy, before finally coalescing into a single, football-shaped elliptical galaxy. Here's the twist, this isn't even our first galactic rodeo. The Milky Way has cannibalized smaller galaxies before the Sagittarius dwarf spheroidal is currently being torn apart by our gravity. But Andromeda is our equal, a mirror spiral with nearly 1 trillion stars. Their merger will fling some stars into intergalactic space while others plunge toward the newly merged core. where twin supermassive black holes will eventually spiral together, shaking space-time with gravitational waves. By then, our sun may have faded, but any remaining civilizations will witness a sky unlike anything humans ever saw, a shimmering blend of two galactic legacies, proving that even in the cosmos, endings are just spectacular new beginnings. Deep in the constellation Centaurus, a young star named V1400 Centauri is crafting a celestial masterpiece that puts Saturn's iconic rings to shame. This stellar toddler, barely 16 million years old, a blink in cosmic terms, boasts a ring system 200 times wider than Saturn's, stretching over 180 million miles across. To put that in perspective, if you dropped this ring system into our solar system, it would swallow Earth's entire orbit with room to spare. Yet what makes these rings truly extraordinary isn't just their scale. It's the tantalizing possibility that they're mid-construction, actively forging moons or even planets right before our eyes. Unlike Saturn's icy bands, V1400 Centauri's rings are made of dust and gas, remnants of the same material that birthed the star itself. Observations reveal bizarre gaps in the ring's clean, dark divisions that suggest unseen objects might be carving paths as they grow. On Saturn, moons like Pan and Daphne's sculpt the edges of rings with their gravity, creating wave-like patterns. Here, the scale is so vast that the hidden architects could be infant planets, their gravitational pull sweeping up debris like cosmic snowplows. Some astronomers even speculate these rings might resemble the early solar system's protoplanetary disk, offering a front-row seat to how worlds like Earth first assembled. The star itself adds another layer of mystery. V1400 Centauri is what's called a T-Tauri star, a type of young, variable sun still settling into stable fusion. Its light flickers unpredictably, sometimes dimming by as much as 75% in mere days. While all T-Tauri stars are prone to mood swings, this one's extreme behavior might be linked to its colossal rings. Imagine thick spirals of dust eclipsing the star's face, or clumps of material casting moving shadows as they orbit. It's a dynamic, messy construction zone, nothing like the serene rings we're used to seeing around mature planets. What's most exciting is the potential for discovery. If moons or planets are indeed forming here, they'd be some of the youngest ever observed, still hot from their violent births, possibly with molten surfaces or thick, primordial atmospheres. Future telescopes might catch these objects in the act of coalescing, giving us unprecedented insight into how planetary systems take shape. And while Saturn's rings are beautiful relics of the past, V1400 Centauri's rings are a living laboratory, a cosmic workshop where the tools of creation are still humming. This discovery forces us to rethink how planetary systems evolve. We've long assumed rings are fleeting features, destined to dissipate or clump into moons within millions of years. But if rings this vast and complex can persist around a young star, they might play a far greater role in planet formation than we ever guessed. Perhaps rings aren't just byproducts, they're cosmic cradles, shaping the architecture of entire solar systems. One thing's certain, the universe has a flair for spectacle, and V1400 Centauri is proof that even its construction sites are jaw-dropping works of art. Deep in the constellation Centaurus, a cosmic ghost stretches its icy fingers through space, the Boomerang Nebula, officially the coldest natural place we've ever found in the universe. Here, temperatures plunge to a bone-chilling 1 degree Kelvin, that's just 1 degree above absolute zero, colder than the frozen void between galaxies and even colder than the faint glow of the cosmic microwave background radiation left over from the Big Bang itself. To put that in perspective, this nebula is colder than any laboratory freezer on Earth, colder than Pluto's darkest shadows, and colder than the vacuum of space should theoretically allow. What makes this place defy the universe's baseline temperature? The secret lies in its violent death throes. The Boomerang Nebula is a preplanetary nebula, a dying star in its final act before becoming a white dwarf. But unlike most stars that shed their outer layers gently, this one is ejecting gas at breakneck speeds over 370,000 miles per hour, causing rapid expansion that chills the surrounding material like cosmic air conditioning. Imagine opening a can of compressed air. As the gas escapes and expands, the can gets colder. The Boomerang Nebula works the same way, just on a stellar scale, with its outflowing gas expanding so fast that it steals heat from the surrounding space. The nebula's eerie shape adds to its mystique. Twin lobes of gas stretch outward like a cosmic hourglass, though from our vantage point, it appears bow-tie-shaped, hence its nickname. These lobes aren't static, they're filled with turbulent streams of gas and dust sculpted by the dying star's erratic winds. Hubble Space Telescope images reveal intricate patterns within the lobes, like frozen smoke caught in a stellar breeze. And here's the twist, that smoke is actually microscopic dust grains, flecks of carbon and silicate floating in gas so cold that atoms almost stop moving entirely. What fascinates scientists isn't just the record-breaking cold, it's how the boomerang challenges our understanding of thermodynamics. The cosmic microwave background, the afterglow of the Big Bang, permeates all space at about 2.7 degrees Kelvin. Normally, nothing in nature dips below this universal baseline, yet the Boomerang Nebula defies the odds. Its rapid expansion creates a localized pocket where the rules bend, proving that even the universe's most fundamental constants have exceptions. This cosmic deep freeze won't last forever. As the central star continues to evolve, its outbursts will eventually slow, allowing the nebula to warm to match its surroundings. For now, though, it stands as a fleeting monument to nature's ability to push limits, a place where the very concept of cold gets rewritten. So the next time you shiver on a winter night, remember, there's a patch of space out there where winter never ends, and it makes Earth's coldest day feel like a tropical paradise. Most planets are content with a single moon or a symmetrical family of them, but Mars keeps two oddballs in orbit, each dancing to its own erratic rhythm. Phobos, the inner moon, races around the red planet so fast it outpaces the Martian day, rising in the west and setting in the east twice every 24.5 hours. Its frantic orbit, just 3,700 miles above the surface, means Martian explorers would see it streak across the sky in a blur, completing a full cycle in less than 8 hours. Meanwhile, Deimos, its distant sibling, takes a leisurely 30 hours to circle Mars, drifting so slowly it appears almost stationary against the stars. Together, they're less like siblings and more like strangers sharing a bus stop, one tapping its foot impatiently, the other lost in daydreams. What explains this bizarre mismatch? The leading theory suggests both moons were once free-roaming asteroids, captured by Mars's gravity during the solar system's chaotic youth. Phobos and Deimos share the dark, carbon-rich composition typical of asteroids from the outer asteroid belt, and their irregular, potato-like shapes betray origins too small for gravity to sculpt them into spheres. But how they ended up in such contrasting orbits remains a puzzle. Some models propose a violent collision near Mars shattered a single captured asteroid, scattering debris that later coalesced into the two moons. Others suggest they were snagged separately, with Phobos getting dragged inward over eons by tidal forces while Deimos resisted the pull. The differences don't end with speed. Phobos, the closer moon, is literally falling apart. Tidal forces from Mars are gradually tugging it downward, lowering its orbit by about 6 feet every century. Within 50 million years, a blink in cosmic time, it'll either crash into Mars or be shredded into a fleeting ring. Deimos, by contrast, is inching outward, destined to one day escape Mars's grip entirely. This divergence highlights a cosmic truth: proximity is destiny. The same forces that doom Phobos barely touch its distant twin, as if Mars has one moon on a leash and another slipping through its fingers. Yet for all their differences, these moons share an eerie role in Martian skies. Phobos's speedy trance, its mean it occasionally eclipses the Sun, but its small size leaves the Sun peeking around its edges, creating a fiery ring rather than true darkness. Deimos, though slower, is so far away it appears barely larger than a bright star, casting no noticeable shadow. Future colonists might watch Phobos's hurried eclipses like clockwork, while Deimos lingers as a faint, unchanging dot, one moon a metronome, the other a barely moving watermark on the horizon. Their origins as captured asteroids offer a glimpse into the solar system's ruthless efficiency. Mars, too small to form moons naturally like Earth or Jupiter, improvised by stealing passing rubble, a cosmic scavenger turning debris into companions. If we ever explore their surfaces, we might find them more akin to asteroids than traditional moons, their dusty exteriors preserving ancient secrets from the asteroid belt. For now, they serve as reminders that even in the orderly solar system, some worlds make do with borrowed treasures, dancing to rhythms no planet could ever compose. Stretching across an unimaginable 10 billion light-years, the Hercules Corona Borealis Great Wall isn't just a structure, it's a cosmic contradiction. This colossal filament of galaxies, the largest known arrangement of matter in the universe, defies one of cosmology's foundational ideas, that the universe should look roughly the same in all directions on the largest scales. Yet here it is, a sprawling, uneven web of superclusters and voids so vast it would take light, the fastest thing in existence, 10 billion years to traverse it. To put that in perspective, this single structure spans a tenth of the observable universe's diameter, a scale so immense it challenges our understanding of how matter clumped together after the Big Bang. How could something this enormous exist within the framework of cosmic inflation? The prevailing theory suggests that in the universe's earliest moments, space expanded faster than light itself, smoothing out irregularities and creating a mostly uniform distribution of matter. But the Hercules Corona Borealis Great Wall, discovered in 2013 by mapping gamma ray bursts the death cries of massive stars, reveals a glaring anomaly. These bursts act like cosmic breadcrumbs, tracing the locations of galaxies across billions of light-years, and when scientists connected the dots, they found a concentration of matter so dense and extensive, it shouldn't be possible under standard inflationary models. Some theorists argue this might be a statistical fluke, an illusion created by our limited perspective. After all, we're seeing this structure as it existed 10 billion years ago, and the universe has expanded dramatically since then. Others propose more radical ideas. Perhaps inflation wasn't perfectly uniform, leaving behind defects in spacetime that seeded these titanic structures. Or maybe the wall is evidence of something deeper, an unknown force or interaction that shaped the cosmos in ways our current physics can't yet explain. What's undeniable is the sheer grandeur of this celestial architecture. Imagine standing in the middle of it. Galaxies would stretch beyond the horizon in every direction, not as isolated islands but as a continuous, glowing tapestry, each cluster bound by gravity in a dance lasting billions of years. And yet, despite its enormity, the Hercules Corona Borealis Great Wall is invisible to ordinary telescopes. Its discovery required piecing together the faint afterglows of cataclysmic stellar explosions, a reminder that the universe's greatest wonders often hide in plain sight, waiting for us to decode their secrets. This cosmic behemoth forces us to reconsider the limits of scale. If structures this vast exist, what else might lurk in the unmapped regions of the cosmos? Future surveys with next-generation telescopes could reveal even larger formations, pushing the boundaries of what we thought possible. For now, the Hercules Corona Borealis Great Wall stands as both a triumph of discovery and a humbling puzzle, proof that the universe reserves its grandest surprises for those willing to look beyond the edges of their theories. Imagine waking up to 3 suns in the sky, one rising, one setting, and the third hanging lazily on the horizon. This isn't science fiction. It's the daily reality on HD 131399b, a rogue planet drifting through a stellar menage, a 400 light-years away in the constellation Centaurus. Most planets orbit a single star, but this one is caught in a gravitational tug-of-war between three, creating a celestial ballet so chaotic, its future hangs in the balance between eternal daylight and frozen exile. The star system itself defies expectations. At the center, a primary star twice as massive as our Sun holds court, with two smaller stars locked in a tight orbit around each other, all three dancing around a shared center of gravity. HD 131399b, a gas giant 4 times Jupiter's mass, circles the largest star in an orbit twice as wide as Pluto's, so distant, a single year lasts 550 Earth years. For stretches of that marathon orbit, the planet experiences constant daylight as all three suns glow in its sky. But as it moves, the angles shift, creating surreal triple sunrises and sunsets where the stars chase each other across the horizon in an endless game of cosmic tag. Yet this spectacle comes with a price. The planet's orbit is precarious, teetering on the edge of instability. Computer simulations suggest that within a few million years, a blink in astronomical terms, the smaller star's gravitational nudges could yank HD 131399b from its path, flinging it into the abyss of interstellar space. One moment, it's bathed in perpetual starlight. The next, it's a frozen orphan drifting through eternal night. What's fascinating isn't just the planet's fate, it's how it survived this long. Triple star systems are notoriously hostile to planets, their complex gravity often shredding fledgling worlds before they can form. That HD 131399b exists at all suggests planets might be more resilient or more opportunistic than we thought. Some astronomers speculated could have formed much closer to its primary star, only to be flung outward by a close encounter with another giant planet. Others propose it was born elsewhere and captured by the triple star system's gravity, making it a cosmic wanderer that found temporary shelter. For now, this world remains a testament to nature's unpredictability. While most planets follow orderly orbits, HD 131399b lives on borrowed time, its triple suns a fleeting gift before the darkness claims it. Future telescopes might catch the moment of its ejection, watching as the stars that once warmed it shrink to pinpricks in its sky. Until then, it spins on, a reminder that even in the cosmos, stability is an illusion, and beauty often blooms where chaos reigns. While the moon's sunlit surface bakes under unfiltered solar radiation, its poles harbor pockets of eternal night, craters so deep and steep that sunlight hasn't touched their floors in billions of years. These permanently shadowed regions, some colder than Pluto's surface at -250 degrees Celsius, act as nature's perfect freezers, preserving water ice delivered by comet impacts and solar wind over eons. The discovery shattered old assumptions of a bone-dry moon, revealing frozen reservoirs that could rewrite humanity's future in space. The physics behind these frozen shadows is deceptively simple. Because the moon's axis tilts just 1.5 degrees compared to Earth's 23.5, its polar craters never experience seasonal sunlight shifts. Their rims cast permanent shadows, creating microclimates where temperatures never rise above -170 degrees Celsius, cold enough to trap volatile molecules indefinitely. Instruments aboard NAS, a lunar reconnaissance orbiter, detected hydrogen signatures in these craters, later confirmed as water ice by India's Chandrayaan-1 mission. Some deposits are remarkably pure, like frost glinting in the darkness, while others mix with lunar soil in a concrete-like blend. What's revolutionary isn't just the ice's existence, it's the scale. Shackleton Crater alone, a 12-mile-wide chasm near the South Pole, may hold enough frozen water to fill 1,500 Olympic swimming pools. When sunlight glancing off nearby peaks illuminates its depths, orbiting spacecraft glimpse eerie blue patches, the telltale reflection of ice older than Earth's earliest dinosaurs. Beyond water, these shadows likely preserve other cosmic treasures: methane, ammonia, and even organic compounds, a chemical time capsule from the solar system's violent youth. This frozen bounty is why Artemis missions target the lunar South Pole. Water isn't just for drinking. Split into hydrogen and oxygen, it becomes rocket fuel and breathable air, turning the moon into a cosmic gas station. Future bases could harvest this ice with thermal miners, heating the soil to extract vapor, then condensing it into pure liquid. Solar panels placed on crater rims, basking in near-constant sunlight, could power these operations while just a few miles away. Robots work in perpetual darkness, shielded from the extreme temperature swings that batter the rest of the lunar surface. The implications ripple beyond logistics. Ice-laden craters might hold clues to how water reached early Earth, locked in their layers like pages in a history book. Some theories suggest the moon's ice is younger than the craters themselves, delivered by comets long after the moon formed. If so, the same delivery system could have seeded Earth's oceans, making these shadowed pits archives of our own origins. Every scoop of lunar ice could contain molecular whispers from the solar system's birth, preserved in a deep freeze older than civilization itself. Yet accessing this treasure won't be easy. The same permanent darkness that preserves the ice creates a nightmare for engineers. No sunlight means no solar power, and temperatures so low that metals become brittle. Rovers will need nuclear heaters or laser-powered energy beams to survive, while astronauts in nearby sunlit regions might peer into these abysses like miners gazing into a frozen well. The challenges are immense, but the payoff, a sustainable foothold beyond Earth, makes these shadowed craters more than curiosities. They're stepping stones to the stars, icy vaults holding both the secrets of our past and the keys to our future. On December 27, 2004, Earth's upper atmosphere briefly convulsed as if struck by an invisible fist, and no one saw it coming. 50,000 light-years away, a dying star's final scream had just reached us. SGR 1806-20, a magnetar lurking in the constellation Sagittarius, unleashed a burst of energy so powerful it compressed our planet's magnetic field and ionized the upper atmosphere in milliseconds. For 0.1 seconds, this exotic stellar corpse outshone the entire Milky Way, pumping out more X-rays and gamma rays than our Sun will emit in its entire 10-billion-year lifespan. All this from an object no larger than Manhattan. Magnetars aren't your average neutron stars, born from supernovas so violent they twist spacetime itself. These cosmic anomalies pack the Sun's mass into a 12-mile-wide sphere while boasting magnetic fields 1,000 trillion times stronger than Earth. If one replaced the Moon, its magnetism would strip the iron from your blood long before tidal forces ripped apart the planet. But what makes them truly terrifying is their capacity for starquakes, cataclysmic ruptures in their crystalline crusts that snap magnetic field lines like overloaded rubber bands. The resulting explosion, a magnetar flare, unleashes energy equivalent to 1 billion atomic bombs detonating simultaneously. The 2004 event was a wake-up call. Though 50,000 light-years distant comfortably outside the Milky Way's bustling core, its gamma-ray spike still triggered radiation monitors on satellites and briefly scrambled long-range radio communications. Had this magnetar been even a tenth as close, say, 500 light-years away, the flare would have chemically altered our atmosphere, triggering ozone depletion on par with a nuclear winter. At 50 light-years, the burst would have bathed Earth in enough radiation to exterminate most complex life in a celestial blink. Here's the chilling part. Astronomers estimate at least 30 inactive magnetars drift undetected within our cosmic neighborhood. Some could be sleeping giants, their next starquake overdue by millennia. The closest known candidate, XTJ 1810-197, lies a mere 8,000 light-years away, close enough for a direct hit to erase modern technology in an electromagnetic apocalypse. Unlike supernova or asteroid impacts, there's no warning. Magnetars don't smolder before erupting. One moment the sky is calm. The next, an invisible tsunami of high-energy particles shreds satellites, fries power grids, and bathes the surface in lethal radiation. Yet amid the doom scenarios lies an ironic twist. Magnetars might also be cosmic lighthouses guiding interstellar navigation. Their predictable X-ray pulses could someday help spacecraft triangulate positions in the void, assuming we survive long enough to harness them. For now, they remain both a menace and a marvel, proving that even in death, stars hold power to shape or shatter civilizations across the galaxy. Deep in the Tarantula Nebula, a star spins with such ferocity it defies the laws of celestial mechanics. VFTS 102, a stellar speedster whirling at 1 million miles per hour. At that rate, its equator streaks through space faster than a passenger jet crosses continents in mere seconds, stretching the star into an oblate shape so extreme, it's nearly flinging its outer layers into space. If our Sun rotated this fast, it would complete a full spin in just 25 minutes instead of 25 days, its surface plasma slung outward in a glowing, red-hot skirt. What could possibly accelerate a star to such dizzying speeds? The leading theory paints a dramatic origin story. VFTS 102 was likely the survivor of a cosmic cannibalism. Picture two stars locked in a close binary embrace, one gradually siphoning material from its companion. When the donor star exhausted its fuel and exploded as a supernova, the sudden loss of gravitational tether sent the remaining star careening like a slingshot released at full tension. Conservation of angular momentum, the same physics that makes a figure skater spin faster when pulling in their arms, sent the star's rotation into overdrive, its outer layers now barely clinging to the core against centrifugal forces strong enough to tear worlds apart. The evidence for this violent past lingers in VFTS 102's surroundings. The star rockets through space at 160,000 miles per hour, trailing a bowshock of stellar wind like a ship plowing through cosmic waters. Nearby, a pulsar, the dense, rapidly spinning corpse of its former partner, whirls in eerie synchrony, a silent witness to the cataclysm that birthed this stellar fugitive. Together, they form a cosmic crime scene where gravitational forensics tells a tale of theft, destruction, and ultimate escape. Yet this star's breakneck spin comes at a cost. Models suggest its equator experiences gravity reduced by 30% compared to its poles, allowing heavy elements like nitrogen to bubble up from the interior while hydrogen sinks, an atmospheric stratification never seen in slower spinning stars. The extreme forces might even trigger localized nuclear reactions along the equator, creating a patchwork of unstable burning that flickers like a cosmic disco ball. What's truly humbling is imagining the view from a hypothetical planet orbiting this stellar dynamo. The sky would warp visibly as the star's distorted shape loomed overhead, its poles searing hot while the bulging equator cooled into darker bands. Tidal forces would render any orbit unstable, either spiraling into destruction or being flung into the void. VFTS 102 is a reminder that the universe doesn't just create stars, it engineers daredevils, celestial acrobats dancing on the edge of self-destruction. This discovery forces us to reconsider stellar life cycles. Not all stars age gracefully. Some, like VFTS 102, are forged in violence and live on borrowed time. Current estimates suggest it might shed its outer layers entirely within 1 million years, spinning down as it loses mass or potentially collapsing into a magnetar, another cosmic oddity born from extremes. For now, it streaks through the cosmos as a warning and a wonder, proving that even the most fundamental laws of physics have room for spectacular exceptions. In the vast web of the cosmos where galaxies cluster like bustling cities, there exists a desert so vast and empty it defies comprehension, the Boötes void. Spanning 330 million light-years, this spherical chunk of the universe isn't just sparsely populated, it's nearly barren. While typical regions of space host thousands of galaxies, the Boötes void holds perhaps 60 at most, leaving it 1% as dense as the cosmic average. Picture standing in the middle of a football stadium designed to hold 80,000 people, but instead of a roaring crowd, you'd find 3 people scattered in the nosebleed seats. That's the level of desolation we're talking about. The discovery of this void in 1981 sent shockwaves through cosmology. How could a structure this large, this empty, emerge from a universe thought to distribute matter relatively evenly? Some astronomers dismissed it as a statistical fluke, a rare but inevitable gap in the cosmic web, like finding an unusually large bubble in a sheet of bubble wrap. Others saw something more troubling. If voids this size contradict our models of cosmic structure formation, could they hint at forces or phenomena we've yet to account for? One radical hypothesis suggests the Boötes void might be the imprint of an ancient collision with a parallel universe, a bruise left in space-time from a multiversal fender bender. While this idea remains speculative, it underscores how deeply the void challenges our understanding. More mainstream theories propose it's a supervoid, a region where dark energy's repulsive force overpowered gravity early on, pushing matter away before galaxies could form. Supporting this, measurements show the void is slightly cooler than surrounding space, a fingerprint of photons losing energy as they traverse the underdense region, a phenomenon known as the integrated Sachs-Wolf effect. Yet the void isn't entirely lifeless. The few galaxies that do cling to existence here are oddballs, isolated, gas-poor, and often weirdly shaped like survivors of a cosmic shipwreck. One, dubbed the loneliest galaxy, sits so far from its neighbors that its night sky would appear almost entirely black, a single smear of stars against endless nothingness. Studying these galactic castaways offers clues about how galaxies evolve in extreme environments, stripped of the interactions that typically drive star formation and mergers. What unsettles scientists most is the possibility that the Boötes void isn't unique. Larger voids may lurk beyond our observational limits, their emptiness stretching even further. Future telescopes like the Vera Rubin Observatory could reveal whether this void is a bizarre outlier or part of a pattern, one that might force us to rewrite the story of cosmic evolution. For now, it stands as a haunting reminder that the universe isn't just stranger than we imagine. It's stranger than we can imagine, with deserts vaster than any mind can grasp. Billions of years before the first stars flickered to life, before galaxies spiraled into existence, the entire observable universe was compressed into a space smaller than a single atom, a singularity of infinite heat and density. Then, in less than a trillionth of a second, it exploded outward, birthing space, time, and matter itself. That cataclysmic moment, the Big Bang, left behind a ghostly fingerprint still detectable today, the cosmic microwave background, a whisper of radiation that permeates every cubic inch of the cosmos. Imagine turning on an old television to static. About 1% of that snowy interference isn't random noise. It's the literal afterglow of creation, cooled and stretched over 13.8 billion years into faint microwave ripples. This cosmic backdrop wasn't discovered by accident. In 1965, Bell Labs engineers Arno Penzias and Robert Wilson stumbled upon it while troubleshooting a persistent hiss in their radio antenna, a noise that stubbornly lingered no matter where they pointed it or how thoroughly they cleaned out pigeon nests. That noise turned out to be the most important static in history, the oldest light we can observe, emitted when the universe was just 380,000 years old and hot enough to glow like the surface of a star. As space expanded, that primordial light stretched from visible wavelengths into microwaves, preserving a baby picture of the cosmos in exquisite detail. What makes this glow more than just a relic? Its imperfections tell the universe's origin story. Tiny temperature fluctuations, variations as small as 1 part in 100,000, reveal where matter was slightly denser in the early universe. These microscopic ripples seeded everything we see today. The galaxies, clusters, and voids sculpted by gravity, amplifying those initial imperfections over eons. Without those faint variations, matter would have spread evenly, leaving no gravitational footholds for stars or planets to form. The cosmic microwave background is effectively the universe's blueprint, its subtle patterns encoding the ingredients and structure of all existence. Modern telescopes like the Planck satellite have mapped this radiation with unprecedented precision, revealing surprises that still baffle cosmologists. The universe appears slightly lopsided in one direction, an anomaly dubbed the axis of evil, and large-scale structures align in ways our current models struggle to explain. Some speculate these quirks hint at a universe far larger than what we observe, with our cosmic neighborhood just one patch in an infinite multiverse. Others propose exotic physics like dark energy evolving over time or primordial magnetic fields bending light in unexpected ways. Yet beyond the mysteries, the cosmic microwave background offers profound perspective. It's the ultimate time capsule, a snapshot of the universe before the first sunrise, before the first atoms combined into molecules, before the cosmic dark ages gave way to the dawn of starlight. Every direction we look, we're gazing back to that pivotal moment when the fog of plasma cleared and light first traveled freely. And here's the humbling truth. You're made of the same stuff as that ancient glow. The atoms in your body were forged in the Big Bang's aftermath, recycled through stars, and assembled into consciousness over billions of years. So while we marvel at black holes, diamond planets, and singing stars, this faint microwave whisper remains the ultimate touchstone proof that the entire universe sprang from a single, unimaginable event. It's the bedrock of cosmology, the foundation upon which all other cosmic wonders rest. And as technology advances, who knows what other secrets this afterglow might reveal? The universe's first light still has stories to tell, and we've only just begun to listen. From raspberry-scented nebulae to diamond hailstorms on Neptune, the universe has shown us just how wild reality can be. Who would have guessed that black holes hum deep, resonant notes, or that entire planets could be flung into the abyss like cosmic runaways? We've explored worlds where glass rains sideways, stars spin faster than a jet engine, and galaxies vanish into voids so vast they defy explanation. Every discovery peels back another layer, revealing just how little we truly understand and how much wonder is still waiting in the dark. The beauty of space isn't just in its scale, but in its sheer creativity. It doesn't just follow the rules, it rewrites them. A planet made of diamond, a nebula colder than the vacuum of space itself. These aren't exceptions, they're proof that the universe loves surprises. And the best part, we've only scratched the surface. With every telescope we build and every probe we launch, we uncover something that makes us rethink everything we thought we knew. So now it's your turn. Which fact left you staring at the screen in disbelief? Was it the great attractor pulling our galaxy toward the unknown, or the rogue planets drifting eternally through the void? Drop your favorite in the comments and let's geek out over the cosmos together. And if there's a space mystery you're dying for us to explore next, shout it out. The universe is a big place full of stories we've yet to tell. Until then, keep looking up, because out there, somewhere, another mind-blowing secret is waiting to be found.